Welcome everyone to part 3 of the 7.3 notes. So we're looking at example 3, the integral of dx over the square root of 25x squared minus 4. Let's go ahead and switch to gray. Now here the x squared comes first, and then we have the constant subtracted from it. So this is a case where we're going to want to use secant theta. Now the only thing is we haven't seen exactly a case like this. One thing we can do is a little bit of pre-processing so that we don't have a coefficient in front of the x squared. That'll help us when we try to make our substitution. So let's do that pre-processing off to the side here. We got the square root of 25x squared minus 4. What we can do is factor out a 25 from both of these terms. Even though the 4 doesn't have a factor of 25 in it, we can still factor out a 25. What's left over will just be 4 divided by 25 when we factor out the 25. It's okay to do that, because if you turn back around and you distribute the 25 back in, you get 25x squared, and then when it distributes to the fraction, the 25's cancel and you just have minus 4. So it's okay to factor things out like this. Factoring is just reversing the distribution process. Now the square root of 25 is 5, and so we just get the square root of x squared minus 4 over 25 left inside the radical. And that's good because now the x squared doesn't have a coefficient in front of it, and so it matches those heuristics that we were given before. Like if you have the square root of x squared minus a squared, well, there's our a squared right there, 4 over 25. We couldn't have done that before because it didn't quite match. It had something in front of the x squared. All right. So what we can do is write what we have so far, which is the 5. So the integral of dx over 5 times the square root of x squared minus 4 over 25. And now we can go ahead with our trig substitution. So let's let x equal a, which would be the square root of that 4 over 25. That's 2 over 5. And we're going to use secant theta. That's the trig function that'll allow the radical to collapse using a trig identity, the Pythagorean identity. Now the dx here will be 2/5 secant theta tangent theta, because the derivative of secant theta is secant theta tangent theta. And one more thing is we'll mention the restriction on theta. For secant, it's kind of a long one. That makes secant theta 1:1 and allows you to drop the absolute value bars in just a moment. Whoops. Okay, need that there. And we'll switch to blue. We'll make the equals a little bit higher. So now we've got, let's see, 2/5 dx gets replaced with 2/5 secant theta tangent theta. We'll put the d theta off to the right side in just a moment. And then we've got 5 times the square root of 2/5 secant theta squared minus 4 over 25. D theta, didn't want to forget about that. Switch to gray, and we'll go ahead and collapse the radical. The radical 2/5 squared is 4 over 25, and then we have secant squared theta minus 4 over 25. So factoring out the 4 over 25, we'll have the square root of 4 over 25 times open paren secant squared theta minus 1. And secant squared theta minus 1, using the Pythagorean identity, becomes tangent squared theta. We just write that off to the side here. The one we're doing right here, the one we're using is tangent squared theta plus 1 equals secant squared theta. So if you solve that for tangent squared theta, you get secant squared theta minus 1. Just subtract the 1 over, and you can replace secant squared theta minus 1 with tangent squared theta. Now that the two terms have collapsed into one term, we can go ahead and take the square root of each of those factors. So we get 2/5 tan theta. Again, we can drop the absolute values that we would normally have there because tangent theta is positive in those two quadrants, quadrant 1 and quadrant 3 that theta is in. Okay, so we collapsed the thingamabob, the radical. It's 11:20 at night. It's time to call things thingamabobs. So now we have the integral of 2/5 secant theta tangent theta over 5 times 2/5 tangent theta d theta. And things are going to start canceling like crazy. I'll do a bright red. So the 2/5 and the 2/5 can cancel. A tangent and a tangent can cancel. And we're left with a secant theta on the top and a 5 on the bottom. Let's go ahead and pull out the 5 as a 1/5. Then we have the integral of secant theta d theta. And the integral of secant theta, as mentioned in example 2, just in the previous part, is ln, absolute value of secant theta plus tangent theta. Close the absolute value, put a plus c. Scroll down to make some room. And now what we want to do is go back to x. So let's go back to x. We have that secant theta is 5x over 2. We get this because the original substitution we made was x equals 2/5 secant theta. So if we multiply both sides by 5 over 2, we get secant theta is 5x over 2. Now we can make a triangle off of that. A little right triangle with angle theta. Now secant, instead of being adjacent over hypotenuse, secant will be hypotenuse over adjacent. It's the reciprocal of cotangent, cosine. So hypotenuse will be 5x, adjacent side will be 2. The third side we can get by using the Pythagorean theorem, and with that we would get the square root of 25x squared minus 4, which if we look back up to the original integral, that was the radical that we had in the original integral. Again, happens all the time. So now that we've got our triangle set up, we can evaluate any trig function we want at angle theta, including secant theta and tangent theta. So that's what allows us to go back to x. So now we've got secant theta, which is 5x over 2, tangent theta, which is opposite over adjacent. So that'll be the square root of 25x squared minus 4 over 2 plus c. And if you want to go ahead and box it like that, that's totally fine. I'll take that. One thing though I'll mention is that you might see the 2's missing from a solution manual, and it'll seem like a big mystery. Where did the 2's go? So I just wanted to show you what you could do to simplify this even further and get rid of the 2's. So this is like some extra steps that the book might take and give you a solution that looks kind of different seeming. All right, so we can say, or write 1/5 times ln absolute value of 5x plus the square root of 25x squared minus 4 all over 2. So bring those two fractions together. And then use a log property So there's a log property that would say the log of the quotient right here, so the log of this fraction right here will be the log of the top minus the log of the bottom. So log of the top minus the log of the bottom. So we'll have 1/5 times open paren ln absolute value of 5x plus the square root of 25x squared minus 4. That was a bad 4. Let me rewrite that. 4. Close the absolute value, then put a minus, and then put ln absolute value of 2 plus c. Now if we distribute the 1/5, we'll get 1/5 ln absolute value of 5x plus the square root of 25x squared minus 4 minus 1/5 ln absolute value of 2 plus c. And here's where the 2 disappears, because if you look at let me choose a good color here. There we go. That's not a good color. Okay. So if you look at the minus 1/5 ln absolute value of 2 plus c, that's just a constant. We could call that plus k right here if we wanted to. Or we could just use c again, like a lot of people do. And so that's where the 2 would disappear. So your final answer could be 1/5 ln absolute value of 5x plus the square root of 25x squared minus 4, close the absolute value, plus c, or plus k, or whatever the constant is. So the constant term with the 1/5 ln absolute value of 2 can get roped into the plus c constant. So I just want to point out that that could happen, and then the 2 will be gone, and you'll now know where the 2 went. Okay, so that's it for example 3 and part 3. Thank you for watching.